Now let's proceed to the second case when displacement versus time is not known, right? So S may not be provided to you as a function of time, and there may be many practical cases in which that will occur actually, because imagine that whenever you have an unconstrained motion where a particle can move from a point A to point B in more than one number of ways, if it is free to move in any path, in that case you may not actually describe its S versus T relationship. You may not describe, because you may not be controlling that motion, and therefore you may not have S versus T relationship. That relationship will mostly be available for cases which have constrained motion. Imagine a part of a machine which is designed to move in a particular speed and path, right? So you know that path already, you know how much time it should take from this to that point. So you can describe its analytical relationship between time and distance, right? But for many unconstrained motions, that relationship may not be readily available, right? So you should have another category of problems in which S versus T is not given, unlike the one which we just saw. Instead, acceleration is given to you, which is a direct result of some applied forces, right? So, for example, let's start with the force which is applied to a particular particle to cause that motion, right? So we all know that force actually causes acceleration, and then acceleration can be given to you with some velocity and S to be determined, right? So acceleration may need to be converted to velocity and then displacement in another category of problems. So we know that this part where F and A relationship is studied, this is currently out of scope of this topic because we are discussing kinematics. This particular part is kinetics, right? So in kinetics, we will be dealing with problems where force is given and you will be actually determining the motion parameters. Acceleration, for example, right, using mostly Newton's second law. But currently imagine a problem where A is given without reference to the force which caused it in the first place, and now you are asked to determine a velocity at a particular time, displacement at a particular time, right? Or with a given A, you are asked to determine velocity when the displacement was that much, right? So any combination of that. So now we will be dealing with problem type 2, in which acceleration is given and you need to integrate that back to velocity and integrate it again back to displacement, right? So second category of problems. So you need to determine the S in those problems by successive integration from acceleration. So previous case was you need to calculate V and A by successive differentiations. Now A is given, so you need to integrate it 2 times to get S. Now that A actually is produced by some forces acting on the moving body. So A is a result of some applied force, but that relationship we will be discussing in a separate chapter. So imagine that just A is given without reference to what force caused that. Obviously there will be some force causing that acceleration, but in kinematics we are mostly interested in the geometry of motion. So we will be simply given with some acceleration and we can be asked to determine V and S. So A is determined by forces acting on moving bodies, and actually we will be discussing that equation in kinetics. So depending upon the nature of nature of the applied forces which produce a particular motion, the given acceleration to you can be a constant value. For example, all free fall cases, I can say that your acceleration is equal to gravitational acceleration, the acceleration of that particle. So it's a constant value, 9.81 meter per second square. Acceleration may also be specified as a function of time, just like displacement was given to you in last case as a function of time. So if that is the case, you can integrate easily 2 times with respect to time to get velocity and displacement respectively. But acceleration can also be given to you as a function of velocity or as a function of position coordinate, right? Or any combination of these quantities. So this actually will make our problem category more complex. It is actually converted into 3 or 4 further types of problems, right? So let me actually define those 4 cases when acceleration is given to you, but it is given to you in different forms. The first case is, let me call it as case A. That case would be when acceleration is given to you in the form of a constant number, right? So case A is acceleration is constant, right? So for example, acceleration is given to you as 10 meter per second square, and you are asked to determine velocity and displacement of that particle, right? So that will be our first case. This case will actually result in a separate problem category, problem type. So case B will be when A is given to you as a function of time. For example, A is equal to 2t square plus 24, right? So a function of time is given and you are asked to determine velocity and displacement. That is another category of problems. The third case will be case C, for example, and that will be A given as a function of velocity, right? And finally case D will be when A is given to you as a function of distance, displacement, right? So A is the function of S, right? So this case is called constant acceleration case, and let's call it as problem type 2, right? Because we have seen problem type 1 when S was given and you have to calculate V and A. Let's call this as that particular category of problem where A is given to you as a function of time and velocity and distance are required. Let's call it as the problem type 3, and similarly problem type 4 and problem type 5, right? Actually all these 4 problem types from 2, 3, 4 and 5, they are actually very similar. In all of these cases acceleration is given but in different forms, right? So I will be discussing the solution techniques for all these 4 cases and then continue with some sample problems in the next session, right? So it is very important that just like I clearly stated what was given, what was required from you, what is the solution technique. So please make that kind of a key or kind of a hint file for yourself for these 4 additional categories also, right? So let's start how we should approach the case A first, right? So let's start with the first case where constant acceleration is given to you, right? Before I start, let me introduce the terminology. So let's say that at t equal to 0 the motion started, and at that time instant when time was 0, velocity is equal to v naught. So v sub naught, I will be using it to denote the initial value of velocity when time was 0, and s was equal to s naught, right? So at any given time t, the value of v will become only v without the subscript naught, and the value of s will be only s without the subscript, right? So now let's see the solution approach which should come in your mind quickly when the acceleration is given in all these additional 4 cases should be what? Successive integration, like 2 times integration with respect to time. Obviously that should work for first 2 cases. Successive integration of acceleration 2 times should work for first 2 cases, because in first case acceleration is a constant number and you know that how to integrate a constant number with respect to a variable time, right? Similarly, if acceleration is already given as a function of time, you should be able to evaluate that integral with respect to time, because it is already a function of time. So you know that how to integrate something which is already in the form of time with respect to time, But the successive integration directly may not work for these two cases, right? In these two cases, the acceleration is given to you as a function of velocity and displacement respectively, and you may not be able to directly integrate that function with respect to time because function is not available in that variable, right? So the solution technique should be successive integration for case A and B, and then we can see later how we should deal with case C and D, right? So successive integration should be done for acceleration, right, to determine S, because we know equation 1 and equation 2. Equation 2 says that acceleration is equal to dv by dt, right? So we can write it as dv is equal to a dt, right? And we can, in the integral form, we can write it as from v naught to v integration, and from the limit should be in t, so t should be 0 to some value of t, right? So that is our equation 1 already, we know that. Now we are given with an additional information that a is constant, which means we can take it out from the integration and simply solve that equation 1 now. So from this side, on the left hand side, we will be having v minus v naught, right, because it will be actually v with limits applied from v naught to v, that will be v minus v naught, right, is equal to a will come out from the integral, and we will simply be having a times t, where limit is applied from 0 to t, right. This should give me simply v is equal to v naught plus at, right. I was able to determine velocity as a function of time by integrating that constant acceleration, right. But this equation will only work for case A, right, when acceleration was constant. So we was able to take it out from the integral. If acceleration was given as a function of time, then that integration will be somewhat complex, right. So that will be case B, not case A. So we were able to solve that integral to determine velocity as a function of time. So now what should we do? Integrate it one more time and to get the displacement, right. So displacement, for displacement we can apply the equation 3, or we can also apply, for example, equation 1 first. So equation 1 is simply v is equal to ds by dt, or in other words ds is equal to v dt. In integral form we write it as from s naught to s, integration of ds is equal to from t equal to 0 to some time t v dt, right. So this is our equation 1 actually in this topic, equation 1, yes, this is equation 2. And let's put that v here, that square, into this equation as a function of time and integrate it one more time as a function of time. So we will be getting displacement, right. So let's see what displacement we get here. So let me write that integral again. ds from s naught to s is equal to v dt from v naught to v, where v is already derived as v naught plus at, right. So let's put that quickly. It will be v naught plus at dt, and t will be from, actually it should be, the limit should be in the form of time, so it's 0 to t, so it should be from 0 to t, and that should give me v naught t, and the limit is from 0 to small t plus at square over 2, right, and then should be from 0 to t, right. On the left hand side I should get s, and that when the limit is applied from s naught to s, that should be s minus s naught, right. The final equation for displacement as a function of time can be written as s is equal to s naught plus v naught t plus 1 over 2 at square, right. That equation should be actually describing your displacement time relationship for a constant acceleration case, right? Since the acceleration was constant value, so we were able to evaluate those successive integrations in this case and derive two equations. One equation is this one on top, which is the velocity time relationship, and then the displacement time relationship also. So what I essentially did is I was given with a constant A, and I converted it into V versus T relationship, and then again converted that one into S versus T relationship, right? That is the summary of whole case A. Now many of the problems involving free fall motion will be actually the cases of constant acceleration, actually the acceleration due to gravity, right? So that should be your solution approach for case A. Let's quickly see the case B and then we can conclude our session here and what solution technique you will be using. And in the next session we will be actually solving 2 or 3 problems for these cases. So I will be picking some representative problem and solving it in the next session. So let's see the case when acceleration was given to you as a function of time. That is also a simple case, right? Because you can again have successive integrations with respect to time to get velocity and distance respectively, right? Only the thing is that now the function is different from problem to problem, right? But it will be some function relating acceleration and time, right? For example, acceleration is equal to minus 3t square, right? So now it's a relationship between t and a. You should be able to integrate that equation 2 times to get v versus t and s versus t respectively, just like you were able to do it for case A, right? So again same method, I quickly do that. Let's apply equation 2 first. Acceleration is equal to dv by dt, right? Or in other words, dv is equal to a dt. In the integration form, it will be from v naught to v from t equal to 0 to a particular value of t, right? If a is given as a function of time, then right hand side of the equation should be very easy for you. It should be that integral should be evaluated automatically. So you can see that if a is some function of time f of t, I can simply have f of t dt from 0 to t, right? Whatever function is given, you integrate it with respect to time, apply limits, and you get a equation in time. On the left hand side, you will be having v minus v naught. So the final velocity time relationship you will be getting is v is equal to v naught plus whatever integration you get from that function f of t dt, right? So that problem, for different problems you will be given different functions. So that part which I am encircling now, that will be different on problem to problem basis, but equation would look like this, right? So this whole thing is actually your v versus t relationship, v versus t relationship. So all the questions like what will be the velocity corresponding to a particular time, or what is the time when velocity was having a particular value, should be answered using that relationship, right? So one more quick thing, finally you can integrate that equation one more time to get displacement, right? So let's apply equation 1 again. Equation 1 was v is equal to ds by dt, or in other words ds is equal to v dt, right? In integration you will be from s naught to s, here it will be 0 to t. So this is same equation 1, this is our equation 1, that was actually our equation 2, right? So this will give me actually s with limits from s naught to s is equal to this integral. So whatever function v versus t you determine from the first part, you just introduce that here in this new integral, right? So this whole square will be actually a function of time. You integrate it with respect to time one more time, right? So that v will be actually should be replaced by this v as a function of time. So you introduce that here and evaluate that integral, you will be getting s as a function of time, right? So it will be, I should write it again, 0 to t v dt, where v will be actually coming from this whole square, right? The relationship will be simply introduced here and integrated it one more time, right? So for case B, we are not able to derive closed form expressions, unlike case A, because here it depends on what function of time it is given, right? But in previous case, since the acceleration was constant, we were able to evaluate the integral, like take it out of the integral, solve that, and finally derive the s versus t relationship. But here I will just keep it as it is and simply tell you that you should use that approach for any given function of time to determine s versus t relationship finally. So at the bottom it will become s minus s naught is equal to this integration again, right? So finally s will be s naught plus that integration of velocity with respect to time from 0 to t. So that which I am encircling now should be your final relationship between s and t, right? So all those questions in which you are asked with what will be the time corresponding to that displacement for a given acceleration given as a function of time, or what is the for example displacement at a particular time, all those problems should be solved using that equation, which you can derive on problem to problem basis depending upon what function that is, right? So is the solution approach clear for case A and case B? They are very similar in nature in a sense that successive integrations are possible. But what if the acceleration is given as a function of velocity? Now you cannot integrate that function as a function of, with respect to time, right? So you need to introduce some modification in the solution method that we will be discussing in the next session, right?